Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and as we always have, we've got another great hangout planned for you this week. Astronomers using the Hubble Space Telescope have produced new maps of our planet, of our own solar system, the largest planet in our solar system, Jupiter. And this will be the first in a series of annual portraits that are going to be taken through a special program. And we're going to talk about some of the people who have been responsible for these images in just a bit. But before I get started, we have one announcement. On October 19th, the White House is hosting an astronomy night, and while you personally can't go, I think it's by invitation only, there are lots of people who are going to be able to.
I didn't get my invite either, so no.
Yeah, no, I'm not on the list either. But there are going to be some scientists, engineers, mathematicians, and entrepreneurs that will be on the south lawn of the White House, where they all get to participate in the White House Astronomy Night. But you can participate remotely. If you go to the link, I have the link in the description box of the event page. If you go there and click on it, you can tell them how you plan to participate if you do. One of the ways in which you can participate is by going to something called, there's a second link which I also have on the description box that points to the Center for Astrophysics at Harvard webpage, where you can go on something called the Micro Observatory Network, and you can capture your own images of space using real telescopes that you can control over the internet. So there's lots of ways to interact. Go to those web pages to find out more. This is on Monday, October 19th, and I don't know. Are you going to do anything, Scott? I'm thinking maybe I might. It depends on whether or not I get to this Micro Observatory Network or not.
Maybe we could conspire. We'll conspire.
All right. Anyway, it's good to see the White House and and our government taking an interest in astronomy. So if you want to participate, please do it. Okay, so let's get started with this week's hangout. As I said, I'm Tony Darnell. You guys know who I am. Joining me as he does every week is Scott Lewis. Well, he does most weeks. He was not around last week, but he is this week. And
I missed you. I missed all of the
internet. I missed you too. I had some Hubble Hangout tweets that I missed completely last week because you weren't here, because I couldn't do it all at once. So I'm glad you're back. Carol Christian, who also joins us each week, usually is on travel, but she'll be back next week. We hope to have her back at that time, so she won't be able to join us this time around. Okay, so we want you, as we do with every single Hangout that we do, talk to us. Tell us what you think. Hopefully, you will read your comments and questions on the Hangout, especially if they're about what we're going to talk about, which is the planet Jupiter. So
that helps. Yes,
that's right. Right. I mean, who knows? I mean, I may just read any old random comment. We'll never know. But feel free to interact with us. We hope that you will ask us questions and comments, and Scott will tell you how you can do that.
So the best and easiest way for you to interact with us right now while we're live is, as you're watching us on YouTube, on the bottom left of the live stream, you'll see some yellow text saying that we are answering your questions live. It'll pop up in a brand new window, allow you to ask questions and even upvote other people's questions. We get to see those. We will select those when we're answering them. And so if you did not get to watch us live, you'll see when we're answering those questions. Also, I will be watching over on Twitter. I'm going to be live tweeting some of the images that are going to be going on as we're live using the hashtag Hubble Hangout. And so if you have any questions or comments for any of us or our panelists, please feel free to use that hashtag. We're at Hubble Telescope on Twitter. And we're also on Instagram at Official Hubble. So I put in one of our animations for today's show up on Instagram earlier today. And follow us on YouTube. We are at Hubble Site Channel on YouTube, and so you can see more of our shows in the upcoming future, and you can get notified for when we're live streaming too.
That's right, and the Instagram thing is a pretty recent thing we've got set up. I post on it, Scott posts on it. I have been doing less up, Scott more so than me these days, because of the you can only do it through like iPads and iPhones and stuff, right? I mean, you have to use their app to get it on there, so it's a little bit.
Well, you know. That's why I'm the new hotness and you're the old and busted.
Old and busted. Oh, you had to go there. Thank you.
I had to.
Yeah. Old and busted. I see. Okay. Well, all right. Let's get started. So
I mean, you're refined like a nice wine, Tony. Like a nice wine.
I get better with age. That's right.
Yep. Like some good Thunderbird.
That's right. Where's my hat? Oh, Thunderbird. I'm a marionette now, right? Okay, so here we go. Let's start this week's Hangout. as I mentioned before, astronomers have been using Hubble to look within our own solar system and specifically at the planet Jupiter. And joining me to talk about some of these observations is Dr. Amy Simon. She is an astronomer at the Goddard Space Flight Center. Welcome, Amy. And by the way, everybody here has been on a Hangout before. It's good to have you back. So thank you for joining us again. Dr. Glenn Orton, he's from the JPL, as well as Dr. Mike Wong. He's astronomer at University of California at Berkeley. Hi, Mike, and welcome to all of you. So let's get straight to the map. While Scott's putting it up, I want to talk about these new images that were taken using Hubble. Now, this is going to be part of a new program that I think we'll have Amy discuss in just a little bit. But these maps of Jupiter are something that you've just started putting together. So, Amy, I'm going to turn it over to you. Why don't you describe to us what these are and what we're looking at?
Okay, so let's talk a little bit about what the program is. The program's called the Outer Planet Atmospheres Legacy Program, and the idea behind it is that we would get a yearly look at each of the outer planets so that we could kind of get that that view like you see when you get your annual school pictures for your kids. You can watch them grow up over the years, right? So what we wanted to do was study how these planets change each year. And so in this particular case, this is our observations from January. It's our first set of Jupiter. And what we planned on doing was looking with Hubble, taking several orbits of Hubble, and looking as the planet goes through 2 full rotations. And the idea behind that is that we can generate full global maps of each planet, and we have 2 of them back to back. So we can do full 2-dimensional wind fields, we can look at storms, we can look at changes, and then we can combine this into this big yearly database so we can also see how it changes over time. So that's kind of the idea behind it.
So is the loop that we're looking at actually start again after 2 full rotations?
I think this one is just 1 rotation.
Okay, so this one, so you've got 1 rotation going around and around.
Right, so I have the first rotation up now, and I could bring up the second one later.
But you have 2 full rotations here.
We have 2
what
full
are the
rotations.
What was the difference between the 2, like frame 1 and frame 2? What was the time delay?
So Jupiter rotates in just under 10 hours, and so we tried to get it as close to that as possible, so we didn't basically have much of a gap between one rotation and the next rotation. And that's just so that we can line those clouds back up again and watch them move a little bit. And so what you're looking at now is this rotation where we've taken all of our images, we map each image out, make a big global map, and this is reprojected back onto a sphere.
Okay, I want to show you. I want to look at some of those in just a sec. But I guess my question is the difference between one frame and the next. How much time delay was that? How much did Jupiter rotate during that time?
Okay, so to make up the map, we have 7 orbits of Hubble back to back, and so that's about an hour and a half between each of those. And so we take a frame, we fill up the whole orbit of Hubble. Then it sends the data down. Then we take the next set, and it's about an hour and a half later. So Jupiter's moved about 30 degrees in that time.
Oh, wow. So you took the whole exposure for the entire orbit then?
No, for the entire time we could see Jupiter, and the Earth wasn't in the way, yeah.
That's right, because as we all know, it's in orbit around the Earth, and the Earth is in the way, so we don't get the complete view. Can we take a look at one of the flat images you were talking about? This is one of the things that you put together. This is what I think you started with before you mapped it onto a sphere, which is what we're looking at here. Scott can pull that up while he's doing that. Here we go. So here, this is the actual map you took, correct?
Right. So that's actually both rotations. The top is the first rotation, and the bottom is the second rotation.
And you did this back in January using the WIFC 3 camera, the Wide Field Camera 3.
That's correct.
Okay. And so is it a mosaic? I mean, or is it just does the planet fill the field of view in Hubble, or what is, how did you do this?
Right. So the Wide Field Camera 3 actually has a really big field of view. It's not meant for looking at the planets in particular. It's meant looking at wide fields, and so we can see the entire visible side of Jupiter at one time. But obviously, we can't see the whole planet. We can't see all sides. And so what I do is I take that image and I map it out flat. So it's basically unrolling the image. And I'll essentially get a section of Jupiter at a time, and then I have to mosaic it together, just like you said, to make this full global map. And because we do this in different filters, I actually have black and white maps in each filter. And then I assign different filters to red, green, and blue to make a color image.
Okay.
So it's a lot more convoluted than just going out there with your color camera and taking a picture.
Okay, and so Glenn, let me get you to comment a little bit on what was your role here in the program, and what did you think of these images?
The images are spectacular. My role is essentially going to be sort of starting now, in a sense. We'll be looking at the structure. We have observations, not what we're seeing in the map are just red, green, and blue. That's what our eyes are sensitive to. But we actually have filters that are looking in and out of gas absorption by methane. That will tell us about where the clouds are in the atmosphere. I also, at the same time, took images from a different telescope, NASA's Infrared Telescope facility at the Summit of Mauna Kea, at much longer wavelengths that we see thermal emission. And so we're actually going to tell the depth corresponding to each of these colors in the planet. And that's all just about beginning.
Okay. And Mike, can I get you to comment a little bit? Which was your role and interest in this program here?
Well, I've been studying Jupiter for a while, and I helped to actually program the telescope to take the exposures and doing some of the calibration. But one thing I wanted to point out, these maps that Amy was talking about, how there's a different black and white map in each filter. As part of this OPAL program, we're providing those on the archive page for the community to use. So these are, anyone can download them. They're available in scientific format as well as in TIFF format. So these maps are going to be available each year that we go back and look at Jupiter. Scott, if you, or Elena, if you could make me big, I have a special graphic right here.
Oh, happy birthday, Amy. Okay. Is this you? Really? It's your birthday. I did not know that.
Yesterday.
Oh, happy birthday, Amy.
Mine was 6 days ago, so go us.
I would sing, but I have a feeling we get sharp drop off in viewers, so I probably should refrain from that. So happy birthday, Amy. That's outstanding. Okay. Well, so that would have, and it happened 2 days ago, you said, right? That was your birthday?
Yesterday.
Oh, yesterday. Okay. Because on Tuesday we did this press release where it came out, so just prior to your birthday. So that's
this was still a good birthday present.
Yeah, most definitely. Okay. So this OPAL program that Mike was talking. Oh, and to go back to what he was saying, I'm glad you brought that up. I put the link to the archive where you can download these images yourself in the description box too. It's archive.stsci.edu/opal, and you can go there and get these, as Mike said, both in scientific format and in TIFF format. And if we get a chance, I'll talk about the difference in a little bit. But I want to go back to the maps themselves, Amy. So why are we doing? First of all, I want to talk about why we're doing this. Isn't Jupiter pretty well observed? I mean, we had Voyager 2 go by, and we did take a lot of really great detailed pictures as it flew by back in the 70s. We have a lot, I'm sure, of ground-based telescopes looking at Jupiter constantly. So what is it that is driving this particular observation program with Hubble?
Okay, well, the spacecraft observations, of course, are great, but we don't actually have all that many. We have big time gaps. So the Voyager flybys were in 1979. The Galileo
bit of time has elapsed. Yeah,
a little bit of time. The Galileo mission began in '95, but it did not have a wide field camera, so we only got very close-up views. We didn't get nice maps like this. Whenever we've had a flyby, Cassini flew by in late 2000. We were able to make one of these maps. But really, when you're talking about weather and trying to understand weather systems and atmospheric dynamics, how the winds change, how the clouds change. Looking once every 20 years, which would be kind of like on Earth looking once a year, I'm going to look today and not look again for 20 years and tell you what the weather's doing, isn't a very realistic approach to try and understand how this is working. And so what we found over the years is we were piecing together these little snapshots from Hubble and from these spacecraft, and we would see that things would change on really short times and really long times. But we had so many gaps, we couldn't really follow the trend. And the proposal here was that if we could do this regularly, look at this every single year, it's kind of closer to looking once a month on Earth. Still not as much as we'd like, but an order of magnitude better than what we had. And so that's what we wanted to do, is be able to really look and watch these changes. And the animation that Scott just put up, you can see this is just over that one rotation. So 10-hour separation, you can watch the Great Red Spot rotating. You can see those cloud bands moving back and forth. So there's a lot of motion, a lot of action that goes on all the time on Jupiter, on short time scales, on long time scales.
Okay, wait, let's just dive into this a little bit. So what Scott, we're blinking back and forth between the two complete rotations that were taken with Hubble, and the difference between and basically rotation 1 is one frame, and then rotation 2 is the other frame, and we're already, and you're looking, and this is what you're talking about. You can see the motion involved here. Now, there's a lot of features here, and what he had up, what Scott had up a moment ago was a graphic showing that basically this red spot, which everybody is very familiar with, is about the size of Earth. It wasn't too much larger, but there's lots of other features going on in here. And I guess my question, before I get to some of the features themselves that you were looking at and you were interested in, yeah, here's the graphic where he was, here's the one with the Earth. You can see that the red spot is roughly about the size of that. And there's also there's spots all over the place, actually, which I want to talk about. But I want to go back to this idea of Hubble versus ground-based for just a moment, because are these things, no matter, I mean, we have some of the best ground-based observatories in the world, is it something that, because of the atmosphere, they're not able to see these kinds of details, or they're just more interested in looking at other things? What is Hubble bringing to this, I guess, is what I'm trying to get at.
Yeah, well, you're exactly right. The atmosphere is the problem for the Earth, and so in the visible wavelengths and ultraviolet wavelengths, Hubble really is the best that we have. You can't get these sorts of spatial resolutions from the ground. Now, in the infrared, we have adaptive optics, so some of the ground-based facilities do quite well in the infrared.
And that's what Glenn was talking about.
Exactly. This UV to visible domain is really Hubble's purview.
Okay, so in these particular wavelengths, the kinds of detail that we're seeing is pretty remarkable compared to what ground-based. But I want to and Glenn, I want to go back to this idea about ground-based using adaptive optics in a moment. But Scott, can you go back to that rotation 1, rotation 2 animation for just a minute? And I'd like to have you guys comment, and maybe I'll start with you, Amy, on what are we seeing anything new with these images that we hadn't seen in previous maps? I think, or maybe we should be more general than that before we do that. We should talk first about the details themselves. We see.
Well, Tony, I would like to point out one more advantage of Hubble, which is that you wouldn't be able from the ground to get a full map of the planet like this, because Jupiter's rotating over a period of about 10 hours. But if you're using a ground-based telescope, Jupiter is only up in the sky for a limited part of that. So we would only be able to get part of a rotation from the ground in Jupiter.
Oh, that's a good point. So no matter where you are on because where you are on the planet matters, right? At first, it has to be up where you're looking, and then it has to be up long enough for you to be able to get these rotations, and that's not always possible, like the way Hubble can. That's an excellent point. Thank you, Mike. That's very good. So the continuity of the observations are much more coherent with Hubble than they are with, say, a ground-based observatory. Okay, cool. All right, well, so here's this rotation back of the difference between the two rotations that Hubble saw, I guess, back in January. So, so Amy, can you comment on some of the features here that we're looking at, first of all? Let's do that first.
Okay, so you can see, obviously, the Great Red Spot, or not quite as big, kind of orange spot. That's outlined in the black box there in the middle. And so that was one of the features we certainly wanted to track. You can also see the distinct reddish bands. On Jupiter, you have what we call zones, which are kind of the white regions, and belts, which are the dark regions. And so, you know, when we do these maps, we actually don't know what we're going to see every time we get them, because the belts and zones change color, clouds come and go, little storms pop up. So, you know, one of the interesting things about Hubble and Opal in particular is that every single year it's going to be a surprise when it hits the ground. You know, I sit here and go through every single image while I'm mapping them out, and I'm always surprised by something somewhere in one of them, without a doubt. So, go ahead.
What about these? There's a band of white. Are those white spots along the bottom there too?
Yeah, there's little white storms. Those are about 40 degrees south latitude. Voyager saw those too. There's usually a train of them, but the number of them changes. So sometimes we have more, sometimes we have fewer. You can also see red spot junior, or oval BA, or it has a bunch of different names, kind of to the right and a little bit south of the Great Red Spot. That's the storm that turned red in 2005.
GRS Junior, I like that.
I keep waiting for Pac-Man to come behind those little white storms.
So in the upper left part of the red spot itself, there seems to be a stream of some kind of turbulence or something that's some kind of waves that are following along in that upper dark band. Or is that just is that real? Is that an actual set of turbulence? Do you think it's associated with the red spot? Or
Yeah, it absolutely is. That the big fluffy clouds all to the left of the Great Red Spot there, that's actually the direction the Great Red Spot is moving, so it's pushing into those clouds, and you have jet streams that go around, approach the Great Red Spot and get kind of pushed around it, and it kind of all mixes on that side there. And so most of the times we look, there's turbulence, but on occasionally we look and there's nothing going on there. And,
okay, well, well, while we're on the topic of the basic stuff of these features, John Glasgow on the Q&A app just asked us, what accounts for the banding of the clouds? Is it chemical composition, temperature, rotational mechanics, all of the above, and how much of each? So, what's causing these bands? I mean, you can kind of see that they're counter-rotating. Right? One's going one direction, one's going another, a little bit in these two frames.
Can we use a technical word?
Maybe. Yeah, go ahead.
Chromophores. Chromophores make the colorful, the differences in color.
Chromophores make the differences in color. Okay,
Yes.
well, what's a chromophore?
it's a molecule of color. We don't know what it is.
Oh, okay.
Particle. Or it's a particle. We don't know.
One of the enduring mysteries is what are these made of? What makes the colors of Jupiter?
And do we have any idea yet, or are we still thinking about this? Are we still?
We have too many ideas. That's part of the problem. It turns out almost everything you can have there turns reddish brown when exposed to sunlight. So there's some sort of smogginess, but almost every chemical that we can throw out there does it. So it's trying to figure out exactly which one has been challenging, shall we say. But the reason that you have the white bands versus the red bands is actually cloud height, and it is because you have that alternating back and forth that you were just pointing out. So the regions where the clouds should be upwelling tend to be white, and where it should be cleared out and subsiding is red. So we think the fresh clouds are always white, and then something happens and they either change color or they get coated with material, stuff rains out, we're not sure, and makes these chromophores, and that's what turns other regions red.
So these brighter bands, then, you're saying, are a little bit higher. Their altitude is a little bit higher than the redder, darker things.
Right.
Oh, so if we were to look at this from a horizon point of view, we might see really high clouds, like we would on Earth in a thunderstorm, for example. Excuse me.
More like cirrus clouds.
Or more like cirrus clouds. Okay,
Yeah,
and then
clouds, except by water, instead of water ice particles, they'd be ammonia ice particles.
So if you could take a cross section of this, you would see, and look at it from the side, we'd see varying heights as well.
Yeah, you'd see varying heights, and I kind of tend to describe it like when you're flying in an airplane, right? You'll go through different levels in the atmosphere, and sometimes there's a nice thick layer of clouds, sometimes it's thin and cirrusy, sometimes there's a thunderstorm here and there, and that's probably actually more what you would see, is that all these things are at different heights.
Okay. Well, okay, John, that was a good question. Thank you very much. And there's another one from AstroGirl1 USA. Hi, AstroGirl. It's good. Welcome back. Wants to know, how much longer do you think the giant red spot will last before completely dissipating? First of all, let's go back to this. Is it dissipating? And how do we know? And if so, how long will it have? Do we have any idea?
Okay, well, it is shrinking. We know that. We've known that.
That's right. We've done a hangout on that before.
Yeah, we did. We've known that since the late 1800s. It's been shrinking pretty continuously since then. What we don't know is exactly when it's going to stop. And so a lot of analytical models and computer models have preferred shapes. And the Great Red Spot's not quite down to that yet. So we think it'll, in the short run at least, keep shrinking. Once it hits that kind of preferred point, it might just become stable and stop there. We're not sure yet. Or it could dissipate, a new one could form. We really have no idea.
Right, and as part of the shrinking, it's changing shape and getting more circular. So it's shrinking faster in the east-west direction than it is in the north-south direction. So it's getting rounder over time.
That's right, because I think I remember seeing images of the red spot back in just a few decades ago, where it seemed to be a lot more flatter than it is now.
Yeah. If you look at Pioneer images, it's just like it's a little disturbing because it's so long and sausagey compared to the way it is now.
Yeah. Well, you actually, while we're talking about long and sausagey, you have
Wow, nice segue,
okay, all right, forget that.
How about before we do that?
Before we do that,
I'll do another. I'll do another thing from Twitter about the size of the red spot before we get into long and sausagey. But Samuel de la Riva Jr., wasn't the red spot 3 times the size of Earth some years ago?
Right, that's about the size we always gave during Voyager, and it has gotten smaller since then.
I mean, if you looked at really old photographs or drawings from the 19th century, late 19th century, you'd swear it's the Great Red Sausage. I mean, it's very long, 30 degrees.
All right, that's got to be the more thinking.
You might have thought that was a joke, but it's actually closer to the original reality.
Really? Good. Well, I'm glad that we were able to work that in again.
Right.
But yes, it's
tried to sanitize you.
yeah, thank you.
I prefer chorizo over red sausage.
Okay, well, but there is this. So as Mike was alluding to, there is this connection between how fast things spin and how flat or elongated they become. And you have a. We were looking at it earlier of the rotation rate of Jupiter versus and sort of just it illustrates this concept. So Scott, if you could put that up, I think you know the one I'm talking about, right? Where the oblate spheroid one, and so when things are spinning at certain rates, and as Jupiter, I think Amy, you said the rotation rate of Jupiter was what again?
It's just under 10 hours.
So 10 hours, and here is a diagram showing Jupiter if it were not rotating at all, how round it would be. Well, I'll let Mike describe it. Why don't you go ahead and talk about it, Mike?
Oh, okay. So there's 3 images of Jupiter here. The one in the middle is an actual snapshot of Jupiter that we took with wide field camera 3, and that's the true shape of Jupiter there.
The one in the middle.
Yeah, so that was from 2009. It's actually the first science observations taken with wide field camera 3 were Jupiter. Just turned out that way. The one on the left is what Jupiter would look like if it were a perfect sphere. So that's not what Jupiter looks like, and the reason why is because it's spinning. Centrifugal force kind of stretches it out in the east-west direction. So it's a little bit flattened. In reality, it has a flattening of about 6%. Now on the right, I've made sort of a fake image of Jupiter here, showing what it would look like if it had double the flattening, if it was spinning much faster. I'm not sure the exact rotation period that would cause this, maybe 5 hours or 6 hours, something like that. But we do know that some exoplanets may be spinning a lot faster. Some stars may have oblate shapes like this.
Right, so this isn't outside the realm of possibility here. We've seen lots of hot Jupiters, for example, around other stars did have very fast rotation rates.
Mm-hmm. And Saturn is a little flatter than Jupiter because it's smaller but spinning a little faster. And there are Kuiper belt objects that are spinning very fast and also have these really stretched out shapes.
Okay. All right, so Amy, I want to go back to some of the features of the maps that you made themselves. And when you said we were doing this because one of the important reasons is to sort of get a sense of Jupiter's weather. If you look at the difference between the 2 rotations, you can see the clouds moving. That's essentially Jupiter's weather. What do we know about the weather of Jupiter so far?
Well, we know it's very, very windy. We can pull up the plot that shows the velocities.
Okay.
So the interesting thing about Jupiter and its winds is that they're very strongly east-west. So the wind is always blowing from the east or the west. And it doesn't change much over time. So if you pick the latitude, you'd always have the wind blowing at you at pretty much the same speed from the same direction every single day. And so this plot's a little complicated, but what we have here is a plot of the velocity, so measured by looking at those clouds, versus latitude up the y-axis.
So on the bottom is how fast the winds are going, and along the side or where on the planet it is, where 0 being the equator. Okay.
Right.
That's right, and a minus number means the wind is blowing to the west.
Thank you. That was my next question. Very
so
good.
0, it means it's moving at the same speed as Jupiter's rotating. So Jupiter doesn't have a solid surface. We have to pick a 0. So Jupiter's rotation is 0.
So not a lot is changing here between the different epochs here, between 79, 2000, and 2015. What do you call it? The large scale stuff is more or less the same, isn't it?
Yeah. The general pattern doesn't change. We see little changes in the maximums of the wind jets, and usually we can tie that back to specific cloud features. And so that's one of the things we're still going to be doing. One of Mike's parts of this project is going to be doing this fancy two-dimensional wind field where we can look at exactly which clouds are moving at which speed rather than an average across the whole planet. So we're going to go back and look at that. But yeah, it's remarkably consistent from Voyager and Cassini to now.
One of the things I've always wondered about Jupiter was I started my career in solar physics, and we did a lot. We studied a lot about solar space weather and the cycle of the sun, the solar cycle, and things like that, and where there was this sort of periodic change in the magnetic activity of the sun, which also related a lot to the wind speeds and the solar winds and things like that. And there were quite a big variation over a 11-year period. Here, though, I've always wondered if there was some kind of cycle at work here, and I guess there wouldn't be, would there? I mean, at least as far as the winds on the upper atmosphere seem to be pretty much the same. They don't seem to be diminishing or going down over time.
That's a question for Glenn.
Yeah, exactly.
Is that what you're thinking too, Glenn? That more or less these upper winds they're not changing.
They're not changing very much ostensibly. There are changes that take place in the atmosphere, though we know in temperature that over the long term, 20 or so years of our observations in the thermal, there are sort of things that grow and then diminish 4 to 8, 15-year timescales, which don't always seem to be related to the seasonal changes in the atmosphere. And so we're looking at the variability in winds as well. Amy's done some of this in the past. So the gross structure you're seeing doesn't seem to change much, but whether there's periodicity in that, it would be interesting to actually examine. That's one of the good reasons for doing this kind of annual study from our point of view.
Yeah, that's a good point. So how are these winds measured just offhand? I mean, how do you get these numbers?
So the little plus signs are actual individual wind points where I just checked. I took a cloud and I tracked how far it moved between one map and the next map, and I know the time separation. But to get the overall smooth black line, I actually took the maps and wrote a computer program to slide them against each other and line up each latitude as it best lines up. So it's called correlation, and basically we were trying to find out the best average point for each latitude.
So the two crosses that are near a lot of the peaks, those were actual observations between the two rotations?
Right. That was my hand check to make sure my computer program was doing the right thing.
I see. Okay. And then the other thing was automated to just sort of get an average.
Right.
Okay. Between all of the different frames that you took.
Right. And so if I actually could plot every single wind point, which is what we'll have later on, you'd see that there's actually some variation over that peak. Some points will be a little bit slower. Some will be. Well,
let's go there. Can we put that up? What did you?
Well, we don't have that figure yet, I don't think.
Oh, sorry. I'm sorry. I thought you said you had.
I'm not a magician, Tony.
You don't know that you can't generate the plots now?
In my brain, maybe.
We'll put you on the paper.
That's about it. Don't tell him that.
If you look at that.
Do I want another authorship?
Yeah, don't tell him that. He'll follow you around, try to hold your hand until you do it. So, okay. All right. So,
Tony, the plot there, the fastest jet, the one that sticks the farthest out to the right. Mm-hmm. That's one area where we do see more variation than other areas, and it's kind of a special location on Jupiter. It seems to be the winds there are a little less stable, and we sometimes have outbreaks of super large storms.
Yeah.
And there may be some similarities between these storms and giant storms that, like the one that was seen in Saturn, 2010 and 2011. There was a really enormous storm there.
Okay.
So that's one example of a region where there's change. And actually, if you wanted to go back to the other image where it showed the flattening, because that shows a comparison between the cloud patterns now and in 2009, and you can already see that some of these changes in the cloud colors that Amy was talking about are visible.
Okay.
So sometimes even if the winds don't seem to change their speeds that much, we do still notice bands turning white or brown.
And that would indicate, according to what I think I understood Glenn say, was that these are altitude changes as well.
You know,
It's part
Right.
of it, yeah.
Yeah. Okay. So it's doing a lot all at the same time. Now these went everybody's thumbnails was on the bottom of that. I couldn't see the scale. Was that in kilometers per second? What were the wind speeds?
That was in meters per second. So the
Meters per
maximum wind
second.
speed's about 150 meters per second.
Meters per second. Okay.
So that's pretty fast.
Yeah. I was going to say that's pretty quick stuff. All right. So he's got this up again, and explain and say again what you were talking about.
Well, I don't have control of the cursor here, but if you look first at the equator, there's this really thick white band, right?
Yeah.
So comparing the middle to one of the side images are the current ones. The middle one is 2009. And if you go north of the equator, there's a dark belt.
Yeah.
And then above that, the first white belt. Yeah, right there. So you can see that in 2009, that was a skinnier white belt. Now in 2015, we're seeing a thicker white belt there. And then above that, there's now a white zone, I mean. And then above that, there's a darker belt. So sort of in the north there is where you can see some of these changes in cloud coloration.
So obviously, we're looking at
a feature there, which is that very dark feature in the center of the right-hand side. We call these brown barges, which are not always there. It's very interesting to see.
Mm-hmm.
So they've got
Okay. All right, so there was one other feature I want to get to, and that was something that Voyager found, but hadn't been seen since, right? Does someone want to comment on that? I think it was called a wave. Is that what?
Yeah. Why don't we pull up the black and white image of the waves, the Hubble one?
All right. And so obviously, as Scott's getting this up, let me just comment. We're looking at Jupiter in the upper atmosphere, and we're looking at the weather dynamics from the very top layers. Do you think things? Well, I'll come back to that. So he's got it up now.
Okay. So what we're looking at here is that's those same flattened maps, but just looking at a small section of it. So we're looking at sort of the mid-latitudes on Jupiter, and just plotting a section of it. And what you can see is these little combs, white combs that we drew, mark basically some vertical features in the clouds.
Oh, I see
Now,
them.
this was one of the things that when I pulled up one of the first images, I saw this and I was kind of surprised. We've never seen this kind of wave with Hubble. Now we've looked with Hubble, not all the time, but we've looked on occasion since 1993. So we've never seen this on Jupiter before with Hubble.
So these are very small scale waves.
Very small scale waves, not the smallest scale that we see, but small relative to what we're used to from Hubble. And if you look kind of closely at these two plots, you'll see there's some dark spots. There's one off to the right above this, and then there's kind of other little storms hidden right underneath that wave. So what we think is going on here is that we're actually seeing cyclones forming underneath that wave, and what happens as the cyclone form is it spawns off a wave. And this actually happens at mid-latitudes on the Earth as well. So it's a very specific type of wave that you have to have the right conditions. Obviously, we don't see it all the time on Jupiter. And it spawns this wave-like feature. And so we had never seen something like this before. And when I was looking through the literature about this to see if it had been seen before, it turns out that it was seen by Voyager 2. And so we have another image that Scott can bring up. It shows you the Voyager 2 version. And as Glenn mentioned, we had these cyclones, these brown barges, in this region during Voyager 1 and 2. And we didn't see the wave in Voyager 1. We only saw it in Voyager 2, and it was only where a new barge was forming. And so we really do think this is tied to cyclones actually forming in Jupiter's atmosphere.
Wow, that's amazing. Okay, and here's it.
Yeah, so there's the Voyager 1. You can see it's in there. It's very faint. It's very hard to see. I credit the person who found it because it takes a little bit of imagination.
Yeah. It's almost hard to convince yourself those were some kind of artifact or something.
Yeah, well, I was looking at the first time I saw the mention of it in a paper, I was looking at the reproduction in the paper and I couldn't see it, so I actually had to go back to the Voyager files and pull the image to find that wave.
Oh yeah, that's very subtle. Okay, so and there was also something that was seen in Voyager 2 that we've seen recently, which is this wispy. What is it? A filament? I think it was called in the press release, or a filament on the red spot. Is that right?
Yeah. Do you want to talk about that, Mike?
Okay. Well, that one I don't think that was seen by Voyager. So this is kind of a new feature that we saw.
Oh, that's right. It says that they thought they saw it, but it was a fluke. But it might have been.
Yeah, but that feature we still need to do some more detailed studies because in the Great Red Spot, you have winds spinning around that are as fast as any of the jets on Jupiter. And so the Great Red Spot also, in the past, it sort of had, well, what fluid dynamicists call a hollow. So it's everything, imagine everything spinning around, but sort of a quiet section in the middle where it's not really spinning. So it's sort of like a spinning donut or something. And that filament to the eye looks a little bit like it may be extending into that quiet region. But you can see in these two images that are taken 10 hours apart, there is some rotation there. So we really want to do a more detailed study of the velocities here and see how it's changing over time. It's not really clear what the significance of that filament itself is, but in general, the flow within the Great Red Spot is very fascinating and has some similarities to vortices in the Earth, in the Gulf Stream. There's what we call pancake vortices in the ocean, where the vortex is very large horizontally but thin vertically.
And these are, yeah, this is, and this might become more well known with follow-up observations, correct? We might be able to get a better idea of this.
Yeah, we'll see if it's still there a year from now for the next.
Okay. Well, okay,
you mentioned that this is something that we're able to learn with our jet stream here on Earth. How is that being applied? Like, how is it helping us learn more about the fluid dynamics of our own atmosphere?
Well, I'm not aware of a really close correlation, but it's a thing where these vortices are. I mean, it's basic physics, and people do studies in the laboratory trying to get flows that are similar to what we observe, and those laboratory studies are applicable both to these vortices seen in the ocean as well as these the Great Red Spot and other vortices on Jupiter. And I didn't mean the jet stream in our atmosphere. I mean the Gulf Stream, which is a current that goes in the North Atlantic.
Okay, well, we've got a lot of great questions, and I'm going to get to them in just a moment, but I want to ask one more thing about Opal itself, the survey. When, and Amy, maybe you can comment on this, what's the cadence going to be? This is a yearly thing. We've got Hubble time to look at this now, at least for a couple of years, or how long do we have? How long is Opal going to be taking data?
So Opal started actually in late 2014. So we also have observations of Uranus and Neptune that'll be going up.
Oh, nice.
And the idea is to look at each of those planets every single year, and we'll add Saturn in 2018 after the Cassini mission ends. And this should go until the end of the Hubble mission. So we could have at least till 2020, possibly longer.
So every year we're going to be getting these maps of Jupiter, Neptune, Uranus, and later Saturn.
That's correct.
That's outstanding. Okay,
that's exciting. It's very exciting.
All right. Well, we look for. Well, that means you know what that means. You got to have yearly hangouts now. I mean, we got.
We'll be back.
Okay, good. I'm glad to hear that. So yeah, Scott's got a URL up that I have posted on the description box. So definitely click on this, learn more about what they're doing, and stay tuned because there's a lot more that's coming. Let me get to some of these questions. Cecil Morgan's asking a question I'd like to know the answer to as well. He's asking, didn't the Galileo orbiter get changes on a much shorter time scale over multiple years? I mean, what did Galileo? Surely we got information from that. We didn't even talk about it.
Okay, so Galileo entered into orbit in 1995, and it was there until 2003. So yeah, it had a very long lifetime. The problem we had with Galileo was that we could get very, very short time cadence data on the order of, minutes and track something around the planet. But because its high gain antenna never opened fully, we couldn't transmit it all back to Earth. And so we could only take very limited snapshots, and we had to prioritize which snapshots we took, first of all, and then which ones we could even send back. And so we couldn't look at one region for days on end. We couldn't make long movies. We could only do really short timescale looks at different regions on the planet. And we also had to prioritize between different instruments. There were a number of different scientific instruments on Galileo. And so the camera being one of them, but there was also a thermal instrument, visible near-infrared spectrometer. So we couldn't do everything we would have loved to do with Galileo, unfortunately. So it was kind of the ideal mission, and it was really hampered by that high gain antenna.
All right, for those who don't remember, it was it had this antenna that unfolded and it got kind of stuck as it was doing so, and so it didn't. It sort of always became a limiting factor for the mission and the science that they could do from it. So, so it was a good question. Thanks, Cecil. I appreciate that. So let's go, Glenn. Let me get you to comment a little more about the ground-based follow-ups of these infrared observations. In what way? You said we can get these because using adaptive optics. We can get high-resolution infrared data of Jupiter. So are you guys, is it being coordinated with Opal in any way?
What we're trying to do, well, is an even bigger coordination that was starting to take place at somewhat longer wavelengths than with C3 will work at. We're still getting reflected sunlight.
What are the wavelengths? So like 1 micron, something like that? Or
1 to about 4 microns.
Oh, 4, okay.
Yeah. So we'll be getting, not always with adaptive optics, again with NASA Infrared Telescope Facility, we're just starting to do daily observations at about several key wavelengths, starting actually in November and continuing, I hope, if the proposal goes through next year. That's for support of the Juno mission. Juno is going to be looking at Jupiter, arriving at Jupiter in July 5 of 2016 and start its first scientific orbits on every 2-week cadence starting in November, mid-November of 2016. So we're sort of trying to get a baseline of what we're trying to see in terms of what that's doing. For that, we're getting ground-based observations in that mid-infrared, near-infrared region, possibly with adaptive optics. We're exploring all those possibilities. And with longer wavelengths that are picking up thermal changes in the atmosphere, so we can actually look at what's driving storms and the distribution of minor constituents. That will tell us indirectly where we see winds rising and falling in the atmosphere. That we're only sort of implying by theoretical means at the moment. We just have these reflected sunlight observations.
So in addition to these Opal maps, which you're calling reflected sunlight observations, the infrared maps that you're taking or you're talking about here could be superimposed on these maps to give you some sense of the temperature of these gases or these bands?
Yes, that's right. The ones that are longer than 5 microns are sensitive to thermal emission mostly. Reflected sunlight is just because of the solar radiation is dropping off in intensity, doesn't dominate anymore. So between 1 and 5 microns, we can actually 1 and say 4 microns. So 4 to 5 microns is sort of a transition part of the spectrum. From 1 to 4, we can actually look at use the adaptive optics when we can, but it's a place where we can actually see where we've seen a bigger change in the altitude of the clouds in the atmosphere. There's stronger methane and hydrogen absorption, gas absorption than we see in the with C3 range.
So have these been done yet? Have you been actually doing these observations yet, or is this coming down the pipe?
That's coming up.
Okay, so
we're going to be a big campaign of support for Juno coming up that I'm actually the coordinator for. And in early November, just before one of our big annual meetings, there'll be a workshop that will look at what Juno wants and needs, can use, and who is interested in doing all of this work. We've started all this in the approach phase for next year, so we hope we get those around March time frame, Opal observations of Jupiter, and the ones in April of 2017 that will coincide almost directly with one of the perigeo passes for Juno.
So, Amy, this ought to be a piece of the pie that you'd be pretty interested in, right? I mean, a piece of the wavelength range you'd like to see, correct, with these maps?
Oh, absolutely. There's some information we can't get from the visible wavelengths. So,
right.
Yeah.
So are you guys? So Glenn was telling us about his role in getting ready for Juno. Are you going to be on a part of that? The science team guys? Are any of you guys going to be? Are you going to be just looking at the data as it comes by?
No, I'm not. I'm not part of that science team.
Okay. Okay. So I was just curious. I was seeing if you guys were going to be involved in that, but certainly the data coming from will be interesting.
At the very least, I'll just come crash Glenn's party because I'm really close to JPL. I'm like, hey, Glenn, what's going on? Tell me what's going on.
Well, anyone can come to the workshop, I think.
Okay. Well, here's a question coming from Andrew Planet. Hi, Andrew. Welcome back. It's always nice to get questions from you. He's asking, and this might be something you could answer, Mike, but anybody is welcome. Could some exoplanets be spinning so fast that even though they might be in the habitable zone and of the right size or composition, they are going too fast to sustain life. I mean, this is a question of spin rate versus, I guess, keeping your atmosphere. Is that possible?
I'm not sure that a spin rate would represent a hazard to life. And mostly when we think about habitability, we're not really talking about these giant planets, these gas giants, because there's no ground to stand on, etc. But people have talked about possibly habitable moons around them, like the Galilean moons, or even Endor is a famous habitable moon.
Yeah, well, that's true. The orbits around the moons around these planets would be probably pretty nice for life. But let's imagine for a second you had this one hypothetical planet that was going, what was it, 6 hours, something like that? That'd be one heck of a diurnal cycle for life. I mean, can you imagine? Time to wake up, time to go to sleep, time to wake up. All right.
No, I don't really see that as a problem. I mean, astronauts do fine on the International Space Station, and that's whipping around the Earth every. If anyone knows the answer, just jump in here. But it's pretty fast.
Okay. And we talked about this briefly, but I'll have you guys comment on it one more time. Shamir Nepal is asking on the Q&A app, besides the red spot, there seem to be some white spots down below. What are those? You want to comment? We talked about those a little bit already.
They're actually pretty much the same thing. So most of the rounder spots on Jupiter are anticyclones. So they're high-pressure systems, kind of anti-hurricanes, if you will. And so it's the same idea. It's just they're much smaller, and we don't know why the Great Red Spot is red. We don't know why the smaller one turned red. So, you know, it just happens to be white versions of a smaller Great Red Spot.
Yeah, and I've been hearing a lot about height versus color here. So maybe they're in different heights
well, they're
of the
all
atmosphere.
high. All the anticyclones are high. They all have clouds that tower up a little bit. The Great Red Spot being one of the biggest and strongest, towers the highest over everything else. But yeah, it's the same type of thing. It's just a smaller version.
All right,
yeah, and actually the Red Spot Junior, we took Hubble data to measure it when it changed color. And the thing is, we can use special filters on Hubble to look at the high altitude particles there. And there was no change in the amount or the height of particles before and after it changed color. So height is part of the story, but that doesn't entirely explain the colors.
Oh, that's interesting. So okay, well that's pretty cool. Well, so there you go, Shamir. They're just pretty much the same as the other, and that's related to Ian Harris's comment. Aren't those white spots in the south from Shoemaker Levy 9? And I think we just talked. No, they're not. That he's referring to a comet that was. Observed smashing into Jupiter. When was that again? Was that
1994?
94. That was
remember that?
Yeah, right. So no, unfortunately, it was not that. Those were cyclonic activity. So here's one from Craig Landon.
Those actually appear dark too. So
that's right. That's right.
For an impact site, you're not going to look for a bright white thing.
And so Craig Landon, I don't fully understand this question, but I'm going to ask it anyway because Craig always has good questions. In the absence of barges due to the processing, is the absence of barges due to the processing, or is that related somehow to the rest of the atmospheric changes?
The barges don't actually seem to be there all that often, and so Glenn mentioned the brown barges.
What's a bar? Oh, what are those?
Yeah. If we can pull one of the flat maps back up. During Voyager, we saw these big elongated brown spots in the North Equatorial Belt.
Oh, okay, I missed that. Okay, so
and they were called barges.
Okay.
Somebody named them brown barges, and they're actually cyclonic cells. We saw them pretty consistently during Voyager, and the first time we looked with Hubble, there were none. They were just all gone. And so it's just a matter of whether or not we have that kind of cyclonic cell. And we don't get them as much in that North Equatorial Belt anymore, but if you look to the north of that red belt, you can see there's an elongated little worm.
Yeah, okay.
There. Yeah, that's
on the planet. And actually, part of the answer to this question is if you just take a snapshot of Jupiter, you might not see what's on the other side. So the great thing about Opal is with this program, we're viewing the entire 360 degrees of longitude. So if there is a barge, we'll catch it with this program.
Yeah, they do, from the longer wavelengths, appear to be extremely desiccated, very, very dry areas. And so they're probably very much downwind, cyclonic, as Amy says, but also very strong downwelling winds with capturing air that has just gotten dried out, and they're just pushing their way down. We see them, as Amy says, not very often up where we're seeing them last January, but sometimes in that dark band that's just south of there, the one that's sort of north of the equator, when it's moving, it's thinning out or moving back, that seems to leave some of these cyclonic regions in its wake. So that's actually something I'm in the middle of investigating, and I'll be talking about next month.
Oh, good. All right. Well, thank you, Craig. That was a good question. I'm glad I asked that one. I'm going to check. Well, let me check on YouTube. I'm not seeing anything. Okay, Scott, is there anything more from Twitter? Anything you want to highlight?
Yeah, let me pull this up here. There's a question from Twitter and I love her handle. That's from Julia H. Myers, but her Twitter handle is Fine Woman instead of Fine Woman.
Yeah, she was also in the Periscope. Which
is amazing. Let me pull this up here. So Hubble, what is the best space and corresponding time resolution of Jupiter maps? Is there significant improvement from older maps?
Okay, so the spatial resolution of Wide Field Camera 3 is about the best we've had. It's slightly better, I think, than Wide Field Planetary Camera 2 was. These are all mapped to a consistent spatial resolution. So when I map them out flat, when I unroll the planet, I map it all to the same resolution regardless. And that's about 10 pixels for every degree of latitude. And that's also so we can compare these maps from different eras, from different years of Hubble data. So I would say the resolution of the camera is slightly better, but the maps are approximately the same. It'll look a little finer just because we're not oversampling. In terms of time resolution, we have these 2 full rotations, but each image is separated by a couple minutes minimum, and that's because of the overhead time on reading them out. So it's not the finest time resolution from image to image, just because of the overhead time of the cameras. I don't know if you want to talk about that, Mike.
Yeah, it's something that we don't have to deal with. Like if you use your phone camera, you take a picture, then there's a delay of about a second or something, and then you can take more pictures. But with the Wide Field Camera 3, it reads out, I think it does take about a minute to do that. And sometimes we can speed that up a little bit by using a subarray, just using part of the detector, but it's worth it because the images that come out are, in addition to the high resolution in space with no atmosphere, we're also getting consistent photometry, which is the word we use. That means we measure the brightness really precisely, so we can compare over time whether brightness is changing a little bit or colors are changing. So that's one of the other advantages of
every pixel has a signal in it, and it goes to a corresponding number, and that number actually means something. It's actually got a unit to it, and that's what it means by photometry. You can actually use that brightness to actually get a physical quantity from it. How long did you say? A minute?
I would have to check. It's about a minute.
It's about that.
Is it the old bucket brigade where you go down, you read down all the rows, and each row is read out pixel by pixel, and then you get all the.
Yep. I think columns are read out first.
Oh, the columns are read out. Okay, well, one or the other. But yeah, that's always a limiting factor with astronomical CCDs. But you have these, 12 megapixel cameras. It can take a while for that little camera to read out the signal from the chip and get it out onto your disk or whatever it is you're storing it on your phone, and so it's not a non-zero amount of time, and that of course is always the limiting factor between how fast you can take a picture, that and the exposure time. So good. That was a good question. Okay, so I think that's everything. I don't see anything on YouTube, and I believe we got it all on Hubble. Twitter. All right. Well, so this is a yearly program. Opal, we'll check in with you. Is there a regular time when you're going to be going back? Like this was January, I think you released these images. Is there another time, a year from now or a few months from now, when you'll be starting again?
Yeah. Well, basically, we want to look when the planets are close to opposition. So that's basically the point directly farthest where the sun is behind the Earth, because that gives us the best spatial resolution. It's kind of when we're closest to the planet. So for Jupiter, that's every 13 months. We've already done Uranus twice, and we have Neptune now, so we'll be doing Neptune again next fall.
Well, awesome. Well, I hope to see that. Yes, I can't wait to see those maps. Those would be outstanding. So,
Yeah,
all right, well,
chat. Oh, Tony, it's a little embarrassing, but I just wanted to make a quick correction. I did say incorrectly that Saturn's rotating faster than Jupiter. It rotates slower than Jupiter, but it is flatter. That's the reason why I said that. It is flatter than Jupiter.
okay, very good. Thanks for clarifying. And so, okay, I guess that's it. Scott, any other comments or questions from Twitter?
Nope, not from Twitter. I do see one here from the Q&A app about Periscope, and we can just actually do a quick ending on it. But mainly Tony, does a quick pre-show Periscope video, which I trolled earlier today, which was a lot of fun. But where it's more of a Q&A and more of a prepping for that, so you can get access to it on your phone, where you can, so if you have an iOS or Android device, and I think maybe Windows as well, and you can also watch it in your web browser. You just can't comment on the web browser, but you can watch Tony do Periscope Q&As beforehand and watch me be snarky in the comments.
Every Tuesday, every Thursday at 3 o'clock we do the Hangout. I try to do it on Tuesday, so yeah, check it out at Hubble Telescope. Well, we're out of time, folks. Thank you, Scott, for all the work on driving the internet. I want to thank my guests, Dr. Amy Simon, Glenn Orton, and Dr. Mike Wong for joining us. Thank you for these great maps. Thank you for letting us know what you're doing, and please come back and show us the other observations once you get them. You promise you'll do that for us, right? Excellent.
Sure thing.
All right, Hubble Huggers, that's it for this Hubble Hangout. I want to thank you all for watching, and as always, keep looking up.
Looking up.
And what we planned on doing was looking with Hubble, taking several orbits of Hubble, and looking as the planet goes through 2 full rotations. And the idea behind that is that we can generate full global maps of each planet, and we have 2 of them, back to back. So we can do full 2-dimensional wind fields, we can look at storms, we can look at changes, and then we can combine this into this big yearly database so we can also see how it changes over time. So that's kind of the idea behind it.
So is the loop that we're looking at actually start again after 2 full rotations?
I think this one is just 1 rotation.
Okay, so this one, so you've got 1 rotation going around and around.
Right, so I have the first rotation up now, and I could bring up the second one later.
But you have 2 full rotations here.
We have 2
what
full
are the
rotations.
What was the difference between the 2, like frame 1 and frame 2? What was the time delay?
So Jupiter rotates in just under 10 hours, and so we tried to get it as close to that as possible, so we didn't basically have much of a gap between one rotation and the next rotation. And that's just so that we can line those clouds back up again and watch them move a little bit. And so what you're looking at now is this rotation where we've taken all of our images, we map each image out, make a big global map, and this is reprojected back onto a sphere.
Okay, I want to show you. I want to look at some of those in just a sec. But I guess my question is the difference between one frame and the next. How much time delay was that? How much did Jupiter rotate during that time?
Okay, so to make up the map, we have 7 orbits of Hubble back to back, and so that's about an hour and a half between each of those. And so we take a frame. We fill up.
Right. Yeah, like some good Thunderbird.
Where's my hat? Oh, Thunderbird. I'm a marionette now, right? Okay, so here we go. Let's start this week's Hangout. As I mentioned before, astronomers have been using Hubble to look within our own solar system and specifically at the planet Jupiter. And joining me to talk about some of these observations is Dr. Amy Simon. She is an astronomer at the Goddard Space Flight Center. Welcome, Amy. And by the way, everybody here has been on a Hangout before. It's good to have you back. So thank you for joining us again. Dr. Glenn Orton, he's from the JPL, as well as Dr. Mike Wong. He's astronomer at University of California at Berkeley. Hi, Mike, and welcome to all of you. So let's get straight to the map. While Scott's putting it up, I want to talk about these new images that were taken using Hubble. Now, this is going to be part of a new program that I think we'll have Amy discuss in just a little bit. But these maps of Jupiter are something that you've just started putting together. So, Amy, I'm going to turn it over to you. Why don't you describe to us what these are and what we're looking at?
Okay, so let's talk a little bit about what the program is. The program's called the Outer Planets Atmospheres Legacy Program, and the idea behind it is that we would get a yearly look at each of the outer planets so that we could kind of get that that view like you see when you get your annual school pictures for your kids. You can watch them grow up over the years, right? So what we wanted to do was study how these planets change each year. And so in this particular case, this is our observations from January. It's our first set of Jupiter.
left of the live stream, you'll see some yellow text saying that we are answering your questions live. It'll pop up in a brand new window, allow you to ask questions and even upvote other people's questions. We get to see those. We will select those when we're answering them. And so if you did not get to watch us live, you'll see when we're answering those questions. Also, I will be watching over on Twitter. I'm going to be live tweeting some of the images that are going to be going on as we're live using the hashtag Hubble Hangout. And so if you have any questions or comments for any of us or our panelists, please feel free to use that hashtag. We're at Hubble Telescope on Twitter. And we're also on Instagram at Official Hubble. So I put in one of our animations for today's show up on Instagram earlier today. And follow us on YouTube. We are at Hubble Site Channel on YouTube, and so you can see more of our shows in the upcoming future, and you can get notified for when we're live streaming too.
That's right, and the Instagram thing is a pretty recent thing we've got set up. I post on it, Scott posts on it. I have been doing less up, Scott more so than me these days because of the you can only do it through like iPads and iPhones and stuff, right? I mean, you have to use their app to get it on there, so it's a little bit.
Well, you know. That's why I'm the new hotness and you're the old and busted.
Old and busted. Yeah. You had to go there. Thank you.
I had to.
Yeah. Old and busted. I see. Okay. Well, all right. Let's get started. So
I mean, you're refined like a nice wine, Tony. Like a nice wine.
I get better with age. Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and as we always have, we've got another great hangout planned for you this week. Astronomers using the Hubble Space Telescope have produced new maps of our planet, of our own solar system, the largest planet in our solar system, Jupiter. And this will be the first in a series of annual portraits that are going to be taken through a special program, and we're going to talk about some of the people who have been responsible for these images in just a bit. But before I get started, we have one announcement. On October 19th, the White House is hosting an astronomy night, and while you personally can't go, I think it's by invitation only, there are lots of people who are going to be able to.
I didn't get my invite either, so no.
Yeah, no, I'm not on the list either. But there are going to be some scientists, engineers, mathematicians, and entrepreneurs that will be on the south lawn of the White House, where they all get to participate in the White House Astronomy Night. But you can participate remotely if you go. First of all, if you go to the link, I have the link in the description box of the event page. If you go there and click on it, you can tell them how you plan to participate if you do. One of the ways in which you can participate is by going to something called, there's a second link which I also have on the description box that points to the Center for Astrophysics at Harvard webpage, where you can go on something called the Micro Observatory Network, and you can capture your own images of space using real telescopes that you can control over the internet. So there's lots of ways to interact. Go to those web pages to find out more. This is on Monday, October 19th, and I don't know. Are you going to do anything, Scott? I'm thinking maybe I might. It depends on whether or not I get to this Micro Observatory Network or not.
Maybe we could conspire. We'll conspire.
All right. Anyway, it's good to see the White House and the and our government taking an interest in astronomy. So if you want to participate, please do it. Okay, so let's get started with this week's hangout. As I said, I'm Tony Darnell. You guys know who I am. Joining me as he does every week is Scott Lewis. Well, he does most weeks. He was not around last week, but he is this week. And
I missed you. I missed all of the internet.
I missed you too. I had some Hubble Hangout tweets that I missed completely last week because you weren't here, because I couldn't do it all at once. So I'm glad you're back. Carol Christian, who also joins us each week, usually is on travel, but she'll be back next week. We hope to have her back at that time, so she won't be able to join us this time around. Okay, so we want you, as we do with every single Hangout that we do, talk to us. Tell us what you think. Hopefully, you will read your comments and questions on the Hangout, especially if they're about what we're going to talk about, which is the planet Jupiter. So
that helps. Yes,
that's right. I mean, who knows? I mean, I may just read any old random comment. We'll never know. But feel free to interact with us. We hope that you will ask us questions and comments, and Scott will tell you how you can do that.
So the best and easiest way for you to interact with us right now while we're live is, as you're watching us on YouTube, on the bottom